Hello everyone, myself Soumya BJ, Assistant Professor, Department of ECE, SJBIT. I am discussing about the Module 2 topic of microwave and antennas. It is related to microwave network theory and passive devices. Currently, I am discussing about the passive devices. We are discussing about the type of passive device called attenuator. In that, we have got a special type of attenuator called precision variable attenuator. In the precision variable attenuator, it makes use of a circular waveguide section which is called represented as C, and it contains a very thin tapered resistive card R2, both sides of which are connected to axis symmetric sections of circular to rectangular waveguide tapered transitions RC1 and RC2. The center circular section with a resistive card can be precisely rotated by 360 degree with respect to the two fixed sections of circular to rectangular waveguide transitions. The induced current on the resistive card R2 due to the incident signal is dissipated as heat, and it produces attenuation of the transmitted signal. In this precision variable attenuator, the incident TE10 dominant wave in the rectangular waveguide is converted into dominant TE11 mode in the circular waveguide. A very thin tapered resistive card is placed perpendicular to the E field at the circular end of each transition section, so that it has a negligible effect on the field perpendicular to it, but absorbs any component which is parallel to it. Therefore, a pure TE11 mode is excited in the middle section. A precision variable attenuator, it makes use of circular waveguide section C, which contains a very thin tapered resistive card R2, to both sides of which are connected axis symmetric sections of circular to rectangular waveguide tapered transitions RC1 and RC2. The center circular section with a resistive card can be precisely rotated by 360 degree with respect to the two fixed sections of circular to rectangular waveguide transitions. The induced current on the resistive card R2 due to the incident signal is dissipated as heat, and it produces attenuation of the transmitted signal. The incident TE10 dominant wave in the rectangular waveguide is converted into dominant TE11 mode in the circular waveguide. A very thin tapered resistive card is placed perpendicular to the E field at the circular end of each transition section, so that it has a negligible effect on the field perpendicular to it, but absorbs any component parallel to it. Hence, a pure TE11 mode is excited in the middle section. With reference to the figure, if the resistive card in the center section is kept at an angle Q related to the E field direction of the TE11 mode, the component E cos theta parallel to the card gets absorbed, while the component E sin theta is transmitted without the attenuation. Taking into reference the figure B, if the resistive card in the center section is kept at an angle Q related to the E field direction of the TE11 mode, the component E cos theta parallel to the card gets absorbed, while the component E sin theta is transmitted without the attenuation. This latter component finally appears as electric field component E sin 2 theta, sin square theta in the rectangular output waveguide. Therefore, we can express the attenuation of incident wave as alpha is equal to E by E sin square theta. The E will get cancelled, so we have 1 by sin square theta that is equal to 1 by mod of S21. In decibels, this can be expressed as minus 40 log of sin theta that is equal to minus 20 log of mod of S21. Therefore, the precision rotary attenuator, it produces the attenuation which depends only on the angle of rotation Q of the resistive card with respect to the incident wave polarization. and these attenuators are normally matched reciprocal devices, so that mod of S21 is equal to mod of S12 and mod of S11 or mod of S22 is equal to VSWR minus 1 by VSWR plus 1, and whose value is very much less than 0.1. We can express the attenuation of the incident wave as alpha is equal to E by E sin square theta. E will get cancelled, we are remaining with 1 by sin square theta, that is equal to 1 by mod of S21. So, alpha in decibels is equal to minus 40 log of sin theta, that is equal to minus 20 log of mod of S21. Therefore, the precision rotary attenuator, it produces the attenuation which depends only on the angle of rotation q of the resistive curve with respect to the incident wave polarization. And since attenuators are normally matched reciprocal devices, mod of S21 is equal to mod of S12 and mod of S11 or mod of S22 is equal to VSWR minus 1 by VSWR plus 1, which is very much less than 0.1. As you can see here, this is the tapered resistive cards. This is RC1 and this is RC2. In the middle we have C, which is having resistive card R2. This slide represents the precision type variable attenuator. Here R1, R2 and R3 they are tapered resistive cards, and RC1 and RC2 they are rectangular to circular waveguide transitions, and C is the circular waveguide section. Here the VSWR is measured at the input or output port, and the S matrix of the ideal precision rotary attenuator is S is equal to 0 sin square theta 0. The S matrix of this ideal precision rotary attenuator is 0 sin square theta 0. These figures actually represent the polarizations of the radiation with polarization of the signal with respect to the representation with respect to the electric as well as the magnetic field. This is about the precision type variable attenuator constructions as well as its working and some of the parameters of interest with respect to this precision type variable attenuator. Now, let us discuss about one more passive device called phase shifters. A phase shifter is a device which provides variable insertion phase in a microwave signal path without altering the physical path length. When I tell phase shifter, this phase shifter which it provides variable insertion phase in a microwave signal path, and it is done without altering the physical path length. And when we tell phase shifters, most of the phase shifters are pro-port devices, and they are characterized by low insertion loss and low VSWR. They are characterized by low insertion loss as well as a low VSWR. The phase of the microwave signal can be changed by inserting a low loss dielectric material or a ferrite material in the wave propagation path. How actually the phase is being changed by means of the phase shifter is by inserting a low loss dielectric material or a ferrite material in the wave propagation path. Accordingly, whenever we use a low loss dielectric material, the phase shifters are called dielectric phase shifters, and we use ferrite material in the wave propagation path, it is called as ferrite phase shifters. And the dielectric phase shifters are usually reciprocal phase shifters, but when we tell about ferrite phase shifters, they can be reciprocal as well as non-reciprocal both, and this actually depends upon whether the variable differential phase shift through the device is a function of direction of propagation. Depending on whether the variable differential phase shift is a function of direction of propagation, we decide whether it is reciprocal or it is non-reciprocal. The phase shifter is the one which provides variable insertion phase in a microwave signal path, and this is done without altering the physical path length. And usually the phase shifters are two-port devices which are characterized by low insertion loss and low VSWR. The phase of the microwave signal can be changed by inserting a low loss dielectric material or a ferrite material in the wave propagation path. When we use dielectric material, they are called as dielectric phase shifters. When we use ferrite, it is called as ferrite phase shifters. Dielectric phase shifters are reciprocal phase shifters, and ferrite phase shifters can be reciprocal as well as non-reciprocal. Let us discuss about the dielectric phase shifters. The dielectric phase shifter, they can be realized by placing a lossless dielectric slab within a waveguide parallel to and at the position of maximum E field. A dielectric phase shifter realized by placing a lossless dielectric slab within a waveguide parallel to and at the position of maximum E field. A differential phase change is produced due to the change of the wave velocity, which is given by Vp is equal to 1 by square root of mu naught epsilon r into 1 by square root of 1 minus Fc by Fd whole square. And this velocity through the dielectric slab compared to that through an empty waveguide in which epsilon r is equal to 1. The two ports are matched by reducing the reflections of the wave from the dielectric slab to tapered at both the ends. The propagation constant through a length L of a dielectric slab and of an empty waveguide excited in dominant mode TE10 are respectively given by beta L is equal to 2 pi by lambda G1 and beta 2 is equal to 2 pi by lambda G0. Lambda G1 is equal to lambda naught by square root of epsilon r divided by square root of 1 minus lambda naught by 2a square root of epsilon r the whole square. Beta 2 is given by 2 pi by lambda G0. Lambda G0 is equal to lambda naught divided by square root of 1 minus lambda naught by 2a the whole square. Thus, the differential phase shift produced by the phase shifter is delta pi is equal to beta 1 minus beta L minus beta naught into L. This is the phase shifter in which there is a dielectric slab in the middle. This is the permittivity of the free space epsilon naught, permittivity of dielectric is epsilon r. This is one more view, and by adjusting the length L, the different phase shift can be produced. Therefore, the S matrix for this ideal phase shifter can be expressed as S matrix is equal to 0 exponential of minus j delta pi exponential of minus j delta pi 0. Assuming there is no reflections, we take the S11 and S22 value as 0. Here got remaining terms as e power of minus j delta pi, e power of minus j delta pi. Next we have precision dielectric rotary phase shifter. This is one more important type in the phase shifter similar to the attenuator. A precision phase shifter can be designed as a rotary type and uses a section of circular waveguide C containing a lossless dielectric plate of length 2L is equal to lambda G by 2, which is called as half wave 180 degrees. This section can be rotated over 360 degree precisely between two sections of circular to rectangular waveguide transitions A and B, each containing lossless dielectric plates of length L is equal to lambda G by 4 called quarter wave sections oriented at an angle of 45 degree with respect to the broad wall of the rectangular waveguide ports at the input and output. To the incident wave, it is again a dominant TE10 wave in the rectangular guide, and when it comes to the circular guide, it becomes a dominant TE11 mode. The half wave section C, it produces a phase shift which is equal to twice its rotation angle Q with respect to the quarter wave section. Whenever theta is equal to 45 degree, how much is the phase shift that is being provided is 90 degree. Dielectric plates are tapered through a length of quarter wavelength and both the ends are for reducing the reflection due to discontinuity. Similar to the precision type variable attenuator, here also dielectric plates are tapered, and they are tapered by means of quarter wavelength lambda by 4. This is basically again done in order to reduce the reflections which occur due to the discontinuity. This is how the precision dielectric rotary phase shifter looks like. This is similar to the precision variable attenuator. This section, the middle section, can be rotated at an angle of 360 degree. Here we need to consider one important angular representation. Here this angle is the plane of the rotary plate and this is the plane of the input plate. The angle between these two is theta degree, and similar to the variable attenuator, here also there is a circular rectangular to circular waveguide transition at the input as well as at the output, also again circular to rectangular waveguide transition. These two are the dielectric plates which are having a lambda by, which are having a dimensions of lambda by 4. And coming to the E out value with respect to this precision rotary phase shifter, it is given by square root of 2 E naught exponential of j 2 theta into exponential of minus j 4 beta L into h. This is about the discussion with respect to the phase shifters, the different the precision type variable phase shifter, as well as similarly precision type variable attenuator. Thank you.